Welcome back to our series on applied regression analysis. I'm Mark Ledbetter, and this is lecture video 37. We are starting chapter 10, which is multiple partial correlation coefficients. In our last series and in the last chapter, we talked about diagnostics. We first talked about residual analysis to detect outliers, and we used these six methods, and then we assessed linearity, homoscedasticity, and independence assumptions using the graphical analysis of residuals again. And so this is all residual analysis, and we even looked at assessing normality using the residuals. We also talked about some alternate strategies such as transformations. We went over the concept of weighted least squares analysis and did a summary. So in this chapter, we're going to talk about multiple correlation, partial correlation, and multiple partial correlation. Before we do that, I want to cover a very basic but important tool that we use in regression called just simply the correlation matrix. And we use this when we have a y variable. We have a y variable that is, say, our dependent variable. And then we have more than one independent variables. So x1, x2, x3. And what I've done is I've just written out the correlation matrix here in general. So if we have y and y correlated with itself, now these are just simply rho, or I should say r, of x, y in this case. So, or y with xi. Okay, so for y with x1, we have r of y and x1. For x2, r of y and x2. And for x3, r of y and x3. Now, you'll notice that I only put the upper triangular portion of this here. And the reason for that is symmetry. So again, this is y with x1 here. And so it's the same as r of x1y. In fact, I don't change the order because there's no need to, so I simply say r of y x1. And then here is y of x2, r of y and x2, and r of y and x3. And so, and this would be r of x1, x2. This is r of x1, x3, r of x2. I seem to be off. Yeah, so r of x3, x2. So x2, x3, which is, so this and this. So as if we draw down the diagonal, we have a symmetric matrix. And the diagonal of ones is where we are correlating a random variable with itself. And of course, even in a sample, that's going to be exactly 1. So we only have to look at half, either the upper half or the lower half. And so some software will give you the upper half, some software will give you the lower half. And I've written out the correlation matrix for our example, where we had the weight, height, age, and age squared. And again, we could just draw down the center and look above or below. You get the exact same results for this. Okay, so what are we seeing here? We're seeing that weight and height are fairly highly correlated, above 0.8. Weight and age are about 0.77. And weight and age squared is very close to that, 0.767, so very close to the 0.77. And when we look at height with age, then we see a 0.64 in height with age squared. Again, since it's age squared and age, we expect those correlations to be very close in value, and they are, 614 and 615. And then when we look at age and age squared, we see a number very close to 1, which we expect since age squared is used, is made from age, right? So we use age to make age squared. Now, we didn't talk about collinearity. However, when we have a very high correlation between one of the x values, this would be x1, x2, x3, x1, x2, x3. When we see something that's at least over 0.7, so you can depending on the field of application, some places use above 0.7, or some fields use a collinearity cutoff of 0.7. Some use 0.8 to say there's too much correlation between two variables. And if there's too much correlation between two explanatory variables, two x values, then, or x variables, then you need to remove one of them. So in this case, I see that age and h squared are very highly related. I need to remove one. So I'm going to look at y, and I'm going to say which one of these correlates the highest or the best with y. And that turns out to be age. It's just a little bit higher, so I would keep age, and I would remove h squared. Okay? And so this is the concept of collinearity in a nutshell. All right, so if you have, so running a correlation matrix on your, at least your independent variables is very important. It is nice to see, but to decide which one to remove, if you need to remove one, you need to have y in there as well, so that you can say, well, whichever one is more highly correlated with y, that is the one that I want to keep. Okay. So now let's look at something called a multiple correlation coefficient. I believe we touched on this in chapter 6 when we talked about correlation there. So the multiple correlation coefficient, we denote that as a capital R or a little r. The capital R, when we're typing, really helps us see the difference between the subscript and the letter. So, and it helps us know that we're talking about a subscript here. So we're saying y given x1 to x2 to xk. So it's y on all of those, or with those, okay? And all at once. It's y correlated with all of those at once. This is a multiple correlation coefficient. So it's the measure of the overall linear, and yes, liner, you'll see liner a few times through here. I guess spell check realizes that the word liner is a word, but we meant linear. So the overall linear association of one dependent variable with several other independent variables, x1 to xk, is the multiple correlation coefficient. So here we can say, write it, the multiple correlation between y and x1 to xk. It's defined as a regular correlation coefficient between y and y hat. So we simply say y hat, which is the predicted value, right? The predicted value of y. So we're taking the correlation between the predicted value of y and the observed values of y. And so we can substitute into our correlation coefficient, sample correlation coefficient formula, and we, instead of having x here, we'll have y hat I minus y hat bar. And y hat bar is simply the sum of the y hat I divided by n, right? So n I equals 1. And so it's the average, it's simply the average of the predicted values. Okay, so we're treating it just like we would x here. And then we take the square root of the sum of squares between yi and y bar, just like we would in the regular correlation coefficient, but instead of x minus x bar, we have yi hat minus y hat bar. Okay? So this is a very ingenious way of making something that's very complicated into a very simple formula. All right? So if you were to try to write this out using all of these beta naught hats and beta 1 hat x's, this would be very, very complicated looking. Okay, so the square of this multiple correlation coefficient is the same as the coefficient of determination that we introduced earlier. So there's two ways to do the correlation coefficient using the sum of squares. That is SSY minus SSE over SSY. Of course, this numerator is also the sum of squares of the model, so or regression. So very easy to calculate, but it's given to us. So I need to change back to here. So I wanted to point out that here is our data, and we have the observed or y values, yi, I should say yi, and y hat I. For each value of y, there, we plug in the x1 to xk values. In this case, we have height, just height and age. We only did 2. And so we plugged height and age in for each observed value of y and calculated a y hat. And we can see the residual would be the difference between the two, right? And so we see how close or far apart they are to each other. Very close, and let's see, not as close, right? And here, even less close, so further apart there. So some are very close, some are not so close. Okay. So let's see what kind of printout that we would get here. So this is from our analysis of variance, and we see that we have an r squared, not the adjusted r squared, but the r squared here is 0.780. So if we wanted our r, our multiple of y with x1, let's see, just x1 and x2, then we would take the square root of 0.7800, and that gives us about 0.883. So there is the multiple correlation coefficient between weight and height and age. Okay, now let's talk about something called a partial correlation coefficient. So the partial correlation coefficient, now this, you'll notice now on, we have on the left side of the bar, we have y and x given, or with, if you want, z1 up to zp. So we are saying that the partial correlation is a measure of the linear relationship between x and y, now after we control for the effect of the other variables. Okay? So after we control for the effect of the other variables, which are z1 to zp. So now you'll need to let z just represent the vector z1, z2 up to zp. Okay? So when you see just z down below here, where I've done some writing, we're going to let z denote all of those the p variables, z1 to zp. So the square of this partial correlation coefficient is now defined as SS, the sum of squares of x given z1 to zp over the sum of squares error with just z1 to zp in the model. So this is similar to something we did in chapter 9. And we'll talk about this a little bit more. So what we're doing is we are decomposing the sum of squares r into SS of x given z, and this, remember, is z, z1 to zp, and SSR. So SS of x given z is equal to SSR of x and z minus SSR of just z. So if you remember. And then we look at SSR of x and z, and we see that that is the sum of squares regression z plus sum of squares x given z. All right. So just to talk about this a little bit more, and I think I need to write these a little bit, oops, missed it. Write these a little clearer. These are sums of squares. Okay. So when you look at this, we've got SSR of x and z, which is here. And then we'll have SSR of z here, and then SS of x and z here. And so when we can break it down like this, where we're simply adding this to this, these two are independent of each other. As you can see in the triangle here, we have, because we're using square roots, right? So we can make this, we can use this right triangle to talk about the relationship between these, and we'll see that SS x given z and SSR of z are independent of each other, and they're orthogonal if we're talking about matrices. Okay, so these are orthogonal quantities. Okay, but independent, and that makes it nice. We can just add them together once we square them, of course, which is what we've done here. Okay, so now let's look at an example. So r squared of y x1 given x2, so the partial correlation of y and x1 given that x2 is in the model is SS of x1 given x2 over SSE of x2. So we can rewrite this as SSE of x2 minus SSE of x1 and x2. If you remember from chapter 9, this is going to be a smaller quantity. So the more variables that you put into the model, the smaller the sum of squares error gets. And it's the reverse for the sum of squares regression. The more that you put into the model, the bigger that is, and the smaller the ones with fewer variables are. So these are two equivalent in the numerator here. These are two equivalent ways of writing this, and we just leave the bottom the same, SSE of x2. We could rewrite this as SSY minus SSR of x2, but why make it more complicated? All right. So the test for the partial correlation of y and x given that z1 to zp are in the model equals 0 is equivalent to the test that the beta star is equal to 0 in this model. This model where we have beta naught, beta 1 to beta p, and beta 1 z1 to beta p zp, and then this extra term beta star x, okay, and plus epsilon. And so we can actually use this F test which again will be, we can either use the SSE or we can use SSR. So SSE is always given, so we could use that. That would be SSE of Z1 to ZP minus SSE of X and Z1 to ZP, and still over the MSE of Z1 to ZP and X. All right. And this is the same that we did in Chapter 9 with the partial F test. So there's another way to write this partial correlation coefficient, and it's given here. I'll let you look at it if you like. And it's good for computer calculations, but it's quite difficult to visualize, unlike the sum of squares and mean sum of squares. All right, mean square error, mean squares, sum of squares, like we used up here for the F, and of course for R squared. So this is a SAS printout, and so everything from, I believe, here up is the same as before, okay? And so from here down is new. And so this is something in SAS they call Proc Core 1 and Proc Core 2, if you ever use SAS. And so they give you a correlation type 1 and a correlation type 2. It's a squared partial correlation type 1 and a squared partial correlation type 2. So type 1, for the correlation, this is different than the sum of squares. So for type 1, that's added in order, just like the type 1 sum of squares. But type 2 is like the type 3 sum of squares. It's added, variables added last, okay? And so over here, we have the intercept, we have height, which is, say, x1, age is x2, and age squared is x3. And we come over under the partial squared partial correlation coefficient of type 1 here for the height. So for height here. And this is the correlation, the squared correlation between weight and height. So this is a, so R squared of weight and height. And then for age, this is weight, age, given height. So these are type 1, remember? So first you'd have the height in the regression equation, or the correlation, or the, the regression equation first. So the first model with just weight and height. So this is the multiple correlation coefficient for weight and height. Height's in there by itself with weight. And then when we go to the second one with age, this is the weight and age given that height is already in the model. Like I said, variables added in order. And then the third one with age squared is r squared of weight and age squared given that height and age are already in the model. Now let's look at the type 2. I'll have to zoom down a little bit. The type 2, for height, we have here, this would be added last. So weight and height in the model, given that age and age squared were already in the model. And then we go down to age and we get weight and age given that height and age squared are already in the model. And then the last one is, it's the same for both of these. So it's the r squared of weight and age squared given that height and age are in the model. And you'll notice this is the only line where they're the same. Now, unlike the sum of squares, you do not sum these. Okay? They do not have a relationship to each other like the sum of squares do. All right. And so to pull out some of the actual r values, we have to take the square root. So in this case, I have the weight and age given that height and age squared are in the model. So that is weight, age, height, age. So that's this quantity here, which is the 0.0171, and that's a 0.131. And I did another up here, the weight, height, given that age squared is in the model. Weight, height, age squared, that's this first one, 0.46046,181. Square root is about 0.679. Okay. So I hope that helps you read the printouts that you're going to see, probably for the homework. And I hope this partial correlation is making some sense to you. Okay, so we can consider the partial correlation as a correlation of residuals. Okay, so the residuals of the regression. So the squared partial correlation coefficient, we can interpret that as the squared simple correlation coefficient. So to show you what we mean, let's consider a multiple regression of y with x1 and x2. And then suppose we regress y on x2 and we get the residuals yi minus yi hat of x2. Okay? So, and then we further regress x1 on x2, and so we have xi1 minus xi hat 1 of x2, and these are the residuals. And then the squared correlation coefficient between the two sets, or between two sets of residuals, is the squared partial correlation coefficient, r squared of y1 given x2, that is, r squared of x1 given x2 is equal to r squared of y minus y hat of x2 and x1 minus x1 hat of x2. So we have this way of looking at this as a correlation between the residuals. Okay? The relationship shows that the partial correlation measures the relation between x1 and x2 after both variables have been adjusted for their linear relationships to x2. So the relationship, the partial correlation, is the relation between, measures the relationship between y and x1 after both of these variables have been adjusted for their linear relationships to x2, as we see here. I hope that's clear enough to see well. All right. Now, let's talk about the multiple partial correlation. The partial correlation coefficient is a measure of the linear relationship between a dependent variable and two or more independent variables after we control for the effect of even more variables. So what do we mean here? So we have r of y with x1 to xk, and then controlling for z1 to zp. So we square this multiple partial correlation coefficient, and we end up with a familiar relationship. It's SS of x1 to xk, controlling for, or given, z1 and zp are already in the model, over SSE of z1 to zp. So again, we can write this as SSE of Z1 to ZP minus SS of X1 to XK Z1 to ZP over, these are SSEs, right, over SSE of Z1 to ZP. Now, let me check and make sure that I wrote that correctly. I don't want to confuse you. If it's wrong, I'd like to correct it now instead of having to come back later and do so. And so let's take a look at where we've written this up before. So, yes, so this is exactly right. So SSE of Z1 to ZP minus SSE of all the variables. Okay, so that is how you can calculate this using the ANOVA tables. There is another equivalent formula here for this multiple partial correlation coefficient. It's given here. I will leave that for you to peruse on your own. Again, it's good for computer calculations, not so good for visualizing or understanding what's going on. Okay, so we have this test for the multiple partial correlation coefficient. For that being equal to 0, that's equivalent to the test of H naught, the null hypothesis that beta 1 star, beta 2 star, etc., up to beta k star equals 0 in this model where we have first the first Z1 to ZP variables and the intercept, and then we're looking at these beta 1 star x1 plus beta 2 star x2 plus ... beta k star xk. And so we're testing these k variables controlling for the first p variables in the model. And so this F test again is x1, f of x1 to xk controlling for z1 to zp already being in the model. And we have this sum of squares, x1 to xk given or controlling for z1 to zp being in the model, but now we have k of these additional variables we are testing, so we have to divide by k. Before we were dividing by 1. So again, this is going to be SSE of z1 to zp minus SSE of x1 to xk z1 to zp over the MSE with all the variables in the model, zp x1 to xk. All right. And this is the same as we did in Chapter 9, the multiple partial F-test. Okay. So I hope that helps you understand the relationships between correlation and these F-tests and how they all work together. And you may not have known that there were multiple correlation coefficients or partial correlation coefficients and multiple partial correlation coefficients. So please don't forget to scan your lecture notes by midnight, the date listed in the course calendar. If you have questions, please come to virtual office hours. If that doesn't work for you, if you can't make it, then by all means email me, but I need 2 things from you. I need the picture of what work you've done so I can see how you're approaching the problem, and 2, please send me a picture of the problem because I may be away from my computer and not able to see the problem, and I do not have them memorized no matter what anyone thinks. So if you send me those 2 pieces of information, I can help you a lot more quickly and efficiently. So I hope you will take care of yourself, and we hope to see you next time.